Right, and we are off. Welcome back, party people. We are going to be doing 8.8c electromagnetic spectrum. Explore the different wavelengths of the EM spectrum, such as light and radio waves, which are used to gain information about distances and properties of components within our amazing universe. So, bam, here we go. I'm going to switch this to slide. Maybe you'll see it, maybe you won't. Okay, that's weird. Okay, so those of you that are listening, you guys will be able to look at my video and see it. Okay, cool, popped up for y'all. Anyway, journey to the edge of the universe, light years. Yesterday we talked a little bit about how fast the speed of light is, like 90, for example. When we're talking about distances in space, you don't want to use miles or kilometers. I mean, to the moon, to the sun alone, it's 93 million miles away. So that is the closest star. When we're talking about other stars, could you imagine trying to use kilometers or miles? I mean, you're going to be sitting there for 2 minutes trying to say this astronomical number to the person that you're trying to convey this information to if you use kilometers or miles. So scientists have decided to use a term that will make it easier to clarify distances in space. So we've decided to use the word light year. Light year, in a nutshell, is how fast light can travel in a year. So we're talking about the speed of light, which, if you're going scientific, can move at the speed of 3 multiplied by 10 to the 8th power, which in layman's terms, or terms that I could understand, it's 186,000 miles per hour. Clearly, that's super fast. So that's what we're really using when we are determining distances in space, because anything else is insignificant. Because as we know from yesterday's lecture, Components of the Universe, that space is vast and it's filled up of mostly emptiness in between the galaxies and stars and planets and moons and everything else. Anyway, so there's a video here. I encourage you to watch it. We're not going to watch it right now, but it is very cool. Starts you on Earth and backs you all the way up, moving at astronomical speeds to see different characteristics of our universe. So certainly encourage you to watch that. We won't be doing that at this time for time purposes. So fast forward right through that. Again, how far is the light year? Another video. We're not going to watch that one either, but I encourage you to do so. We're going to look at some fun facts. And it's mainly going to be repetitive because I just already talked about it. Light travels faster than anything else we can measure. And again, because distances are vast, that's what we choose to use to describe these distances. Again, light years is a measure of distance, not time, which is a sort of confusion for 8th graders, because you have the term years in the description. When we know years, we think of years as a time. You're 13 years old. You're 14 years old. I'm pretty many years old. So I don't even think that's a description, but I just threw it out there. So we typically use years as a time measurement in our discussions in everyday life. However, when we're talking about space, light years is a distance, not a time. It's the distance light can travel in a year, in 1 year. And of course, I've already talked about how fast light goes. So you can, in 1 year, you can traverse 6 trillion miles. That's a great distance. And then a couple more little points here, and I'll talk about them both. So it takes light 8 minutes to reach the Earth from the sun. So when we talked about the nuclear fusion reactions, the hydrogen turning to He because of the collisions in the sun, and that's the nuclear reaction, and that's the thermal energy, and that's what we feel when we step outside. It takes 8 minutes for that light to reach us. Okay, 8 minutes. So 8 light minutes. Hey, that's right. because light travels at the speed of light. Anyway, so there's another term that you need to be aware of. We've decided here on our planet Earth to call the distance between the Earth and the sun 1 astronomical unit. So that's interesting. So then that's another way to measure distance is by using astronomical units. Again, that's just something that you need to know. I don't know that it's ever been tested, but it's something that you need to know. And then love this graphic that's about to pop up right here on the bottom right of your screen. It says the Milky Way galaxy measures 100,000 light years wide. Here's what that means. If you're on one end of the galaxy and you're traveling at the speed of light, it's going to take you 100,000 light years to get across it. So when you're thinking about movies, Star Wars, Star Trek, some of those other space movies, and people are, they're going into different galaxies or whatnot, clearly they're forgetting science, because you can't even if you're traveling at the speed of light speed, you're not even getting very far. Or we only live 100 years, God willing. So if you're traveling at light speed for 100 years, you haven't gone anywhere. I mean, you really haven't. So if we're ever really going to do any space exploration at all, we have to at least figure out how to travel at the speed of light, and then talk to some other folks on how to warp time and whatever and be able to travel another way. So anyway, sorry to burst your bubbles, or hopefully that inspires you to get to work to get us off this rock, which is doomed. We'll talk about that at a later time. Okay. Can you calculate distances in space? So I'm going to ask you guys to go ahead and try and figure this out, because this is a great question. Star A is a star that is 4.6 light years from the sun. Star Y is 30 times further away from the sun than star A. How far away is star Y from the sun? So I look forward to hearing some of y'all's answers to that, whenever you get the time and the mental capacity and the patience to figure that out. And that is the end. So now we're going to jump into the second half, which is the EM spectrum. So, and away we go. And we'll go ahead and put this on slideshow mode. 30 seconds for your station identification and my drink. Okay. We're exploring how, talked about it earlier, how the different wavelengths of the EM spectrum can be used to gain information about our universe. I'm going to show you how that works here in just a second. This is a great screen. The EM spectrum is one way that scientists gather information about the universe. Go ahead and click that at your convenience. I'm going to share, once again, both of these PowerPoints are going to be in Google Classroom for your viewing pleasure. So definitely click on these. Take your time. Look at them. It's all good. However, let's look at these. This is very testable information here. Radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays. As you move from from left to right on this screen, you can see that, look at it, 10 to the power of 4, and they only get smaller. The waves get smaller, the wavelengths get smaller, and remember that wavelengths are measured from crest to crest, so from one top to the next. And as you go from left to right, they get smaller, but something very interesting happens to these waves. They get much stronger. Think about it. We cook our food in microwaves. Infrared light. Visible. Ultraviolet rays. X-rays. I mean, when you're getting I know a lot of you have probably had an X-ray before. What do? They put that, that lead apron on you to try and keep your body, the rest of your body, safe from these hazardous X-rays. And then even smaller, 10 to the power of -10, you have the gamma rays. And if any of you are familiar with the Marvel universe, of course you know Dr. Bruce Banner. He was messing around with gamma rays in his lab, and he affected the atoms of his body on a nuclei level, which turned him into the Hulk. So gamma rays, incredibly harmful, and created the Hulk. So, you know, that's it in a nutshell. And when you're talking about the size of these waves, you can see that radio waves are the size of buildings. And then you go to microwave and infrared, the size of honeybees, to pinheads, down to X-rays, the size of atoms, and then gamma rays, the size of the nuclei of an atom. And if you remember, back in chemistry, I talked about the atom and how big if we were to blow the atom up to the size of the Cowboys stadium, the whole atom would take up the entirety of the stadium, but the nucleus would be a marble on the 50-yard line. So that's how super duper small gamma rays can be. But they're very, very strong. Their wavelength is the shortest, and their size is the smallest, but they're most powerful. But again, click on that little link. Click here to find out how. Definitely do that. EM waves are a special type of wave that do not require matter to travel through, so they can move through empty space unimpeded for the most part. They are aligned according to wavelength on a diagram called the EM spectrum. Now, we have done some things here on Earth. We've sent waves out to space to try to communicate with all the aliens that are out there. So there, you can definitely do some Google searching on how we have the waves and the messages we've sent out from Earth. So definitely look at that. Fun fact stuff. Different kinds of waves in the EM spectrum have different wavelengths, but they all travel the same at the speed of light. They all do. The smaller the wavelength of an EM, the greater energy it has, like I talked about with the gamma rays. So now they flipped it. They put radio on the right, gamma on the left, but the information is still very, very important. So as you're moving from the right to the left, you have radio, microwave, infrared, and in between infrared and ultraviolet, you have visible. And look at the Roy G. Biv in full effect. You have red, orange, yellow, green, blue, indigo, violet. Roy G. Biv, from right to left, the longer wavelength, lower frequency, lower energy, into the indigo, which is the shorter, higher frequency, higher energy. And then continuing on that bar, you have X-ray and gamma. So it's all the same concept. Nothing has changed. We just added the visible in there, so you have Roy G. Biv part of the process. So now they've flipped it on you again. Now we have radio waves on the left, gamma on the right, and you can see the radio waves 10 to the power of 3, gamma rays 10 to the negative 12. And then you look at the frequency as you move from left to right. You have 10 to the 4 all the way to 10 to the 20. So you can see that it's incredibly frequent, and that's what really gives the energy to the gamma rays. But being able to read this graph like this, I'm telling you, I was looking through some STAR questions earlier. They're always going to be an EM spectrum question that has some type of graphic that you need to be able to read. So definitely pay attention to these 10 to the negative 5. There'll be a question that what type of wave is on the larger scale and about 10 to the negative 4. And so clearly that would be infrared rays. So definitely make sure that you can look at this and that it makes sense to you. If you need any help with it, by all means, come see me. Couple of links here. Very, very cool. The EM spectrum and especially the visible aspect of the EM spectrum has given us some amazing space pictures. You can look at all these different pictures of nebula and galaxies. There's so many, and stars, and the EM spectrum is what allows us to see all of these cool characteristics of our universe. So certainly click here to see what the universe looks like using the EM spectrum. And then yesterday I touched on redshift, and how redshift is part of the evidence that we know that part of the evidence of the theory of the Big Bang. So in the fact that when we look up and we're looking at all these different objects in the universe, that most of them seem to be shifted towards the red end of the spectrum, meaning that everything's kind of going away, moving away, like from the singularity explosion that created our universe. So that will give you a little bit more. If you're still not sure about the redshift, blue shift, click on that to learn a little bit more about the redshift and blue shift. Scientists can use the visible light portion of the EM spectrum to determine what a star is made of. They use a spectrometer and they look at the dark absorption lines, and it's kind of like, and it gives the scientists kind of like a fingerprint of the star. They can tell the temperature of the star by the color it is emitted. We will be, the last lecture that you're going to get from me is going to be on the HR diagram. I wanted to do one specifically for that because there typically will be 2 to 3 HR diagram questions on the STAR test. So I want to be able to break it down in ways that you can focus and understand. So that's your next one, will be coming soon. But stars can be figured out by their temperature and color, and we have placed that all in the HR diagram, again, that you will get more information at a later time. But definitely click on these links to find out a little bit more about these facts. Again, and then this would be some of the information that they would gather from using the EM spectrum, the star's atmosphere, you know, the hydrogen, helium content, which kind of tells us the star's age. If it has a lot of helium content, it's more on the hydrogen content, it's on the younger side of the scale. And if it has more helium, it's on the you know, middle aged or later end of the scale. We are done with HR or EM spectrum and distances in space. We are out. Until next time. See ya.